So till now we have learned about the arithmetic circuit design, performing different operations. Also we have seen an example like S is equal to 0 means A plus B need to perform. S is equal to 1 means it need to perform the A minus B. So here with this example we will be able to identify the combinational circuit to perform this operation. So for that, we need to design a K-map function. A K-map will be designed, and based on that K-map, you will be generating a Boolean function, and based on that Boolean function, um, uh, the combinational circuit that can be used to perform that operation will be decided. So in this, the Boolean function derived was S exclusive or BI. So in this case, this is the circuit that will be designed. So in this, Boolean functions will be like yi is equal to bi exclusive of s, and the input, that is the input of yi, and if you take the input of xi, it will be same as that of ai, and cin will be equal to s, which means that if s is equal to 0, then cin will also be equal to 0. If s is equal to 1, c will be equal to 1. So based on the input S, Cn will be decided. So with these inputs, we can design the logic circuit for this adder and subtractor, addition and subtraction operation. That is, S will be given as an input to this C1 or Cn. So this is a full adder circuit. Since it is a 4-bit circuit, we need to have 4-bit full adders. And x1 and y1, x1 means it will be taking the input directly from a1, x2, x3, x4, they will be taking inputs from a2, a3, a4 respectively, and then related to this yi, it will be taking the input from bi. So the bi input, it will be written in this form. Bi will be taken in this form. That is, yi will be taking the inputs in this form, that is S exclusive or bi. So S and B will be given inside an exclusive OR gate, and then will be given as an input to yi. So this is the case with the once full adder circuit. Similarly, you will be having many based on the number of bits. Corresponding full adder circuits will be drawn similar to this. Okay, so the full adder circuits, if there is any carry, means it will be fed to the next full adder. Like that it goes on, and finally it will be given as a C out. And from each full adder, an output will be given like F1, F2, F3, and F4. So this is the logic circuit design of a bit add, a 4-bit adder or subtractor circuit. So next is the design of logic circuit. So arithmetic circuit we have seen. Next is logic circuit. So 16 logic operations can be generated in one circuit, selected by means of 4 selection lines. In order to implement 16 logic operations, we need to make use of 4 selection lines. Or making use of 4 selection lines, 16 operations you will be able to insert. So if I'm using only these operations, and, or, and, not, if these operations are considered, then it requires only 2 selection variables. But 2 selection variables means 2 raised to 2, maximum 4 operations you can include. So in order to make it as 4, one more operation will be included, that is exclusive OR function also will be included. So this is the logic diagram of the logic circuit. So here we are having, in order to perform the four operations, it makes use of two selection inputs, S0 and S1. And the four operations, it is arranged in this format. 0 indicates OR, 1 exclusive OR, 2 and 3 is not. So this is the function table where 0 0 means it performs the OR operation, 0 1 XOR operation, 1 0 AND operation, 1 1 is NOT operation. Okay. So how the design of arithmetic and logic unit will be implemented. That is, now we are going to combine these operations into a single unit. So arithmetic and logic unit means it performs both the logic circuit. It has both the logic circuit and the arithmetic circuit. So S1 and S0 can be made common to both the sections. Like this diagram. See here. You will be having an arithmetic circuit and a logic circuit will be there, which will be in which S1 and S0 is being shared by both the circuits. And one selection input, that is S2, it helps in determining which circuit to be chosen, either to choose the arithmetic circuit or to choose the logic circuit. With the help of multiplexer, it will take the input, it will be performing the operation arithmetic circuit or the logic circuit. This is one form of arrangement. So the S2 is used to differentiate between the two. The output of logic and arithmetic circuits in each stage, it goes through a multiplexer with the selection variable S2. When S2 is equal to 0, the arithmetic operation will be selected, and if S2 is equal to 1, the logic operation will be selected. So more efficient method is like by inhibiting all input carries into the full adder circuits of the parallel adder. Consider the Boolean function that generates the output sum in a full adder circuit. That is how this is being implemented. So if x exclusive or XOR y XOR cn, if this is the function, if I am taking adder means it will be having an x input, then y is there, and one cn input also will be there. Okay, exclusive or. The input carry cn in each stage can be made equal to 0 when a selection variable S2 is equal to 1. So what does that mean is, if S2 is equal to, we have seen in the previous slide that if S2 equal to 0, it implements what? Arithmetic operation. Arithmetic operation. And if S2 equal to 1, it should perform the logic operation. So in case of logic operation, the carry in can be equal to 0. Carry in can be equal to 0 in case of logic operations. So making it as f is equal to x exclusive x or y. And this means any operation you can include in this. Okay, any logic operation can be included in this symbol. Okay, not only the exclusive or, any logic operation can be represented using this symbol in this slide. This expression is valid because of the property of XOR operation. X XOR y is equal to x, if x XOR 0 is equal to x. Okay, so in this case, this can be possible only if the carry-in signal will be equal to 0. So in order to implement the logic operation, it is better to make the carry-in signal equal to 0 so that all the operations can be implemented in a correct way. So how it can be designed? So first design the arithmetic section independent of the logic section. Without considering the logic section, implement the arithmetic section. And then determine the logic operations obtained from the arithmetic circuit in step 1, assuming that the input carries to all stages are 0. So there, what is related to the input carries will be made to 0, and then try to implement the logic operations in the above arithmetic section. And third step is modify the arithmetic circuit to obtain the required logic operation. First is design the arithmetic section independent of the logic operations. Second is start implementing the logic operations in the arithmetic section by making the input carry to 0. And third is some operations need to be modified to get the result of the logic operations. So how it can be done, we can see with the help, we can see this table, what are the modifications that need to be done. So here, as we have said, in the second step, the carry in will be set to 0. Carry in for all the stages will be set to 0. And this will be done when the S2 signal is set to 0. Select S2 selection input. If it is 0 means we need to set the carry in input to 0. So that is made in the step 2. And then after performing these operations, we can see over here that when xi exclusive or yi operation is performed on ai. Okay. Okay, in a previous slide, this indicates exclusive or only. Okay, y means here we are making use of this exclusive or gate to implement the logic operations. Okay, so in this case, okay, once more. So if xi exclusive or yi, this operation will be performed. The input taken is xi here is ai and yi is 0. So when you perform the exclusive or operation, what happens? You will be getting the result as AI itself, isn't it? AI 0 complement will be 1, so AI it becomes plus 0 AI complement means that term becomes 0 only. So you will be getting AI, which means it performs the transfer operation, isn't it? So, but the required operation is it need to implement the OR operation. Okay, it need to, in case of logic operations, it need to implement OR. But here, if the exclusive OR operation is being performed, it gives the output as AI, that is the transfer operation. So this input sequence, if it is given as an input to the adder, the modification need to be performed. Some modification need to be performed. That is AI plus bi. Okay, ai plus b.